Okay, it's working. I was having issues with OBS. So, okay. Well, things are working now. Good morning, mathematicians. Good morning. Yeah, how's life? What are we doing? We're yapping, as usual. About what? Who knows? Oh, what's this? Oh, these are all my these are all my attempts at starting the stream. I'm gonna have to go delete all of those. Okay. As usual. But let's go see. We haven't collectively visited ArXiv for a little while, so we should go check in on what's been showing up, what people been saying, what people been publishing. And tomorrow there's a new video. I'm hoping today I'll record a video for the week after. Yeah. Oh yeah, look at this. We got infinity going on here. Now open the next screen. Open the next screen. Okay, I'll wait for one more of me to appear, and then I'll go to ArXiv. Will there be one more of me? Yes, there we go. I'm just never not fascinated by these recursive images. Anywho, let's go see what's popping off in Langland's. Okay, there hasn't been anything I haven't personally seen yet. Not that I understand or have read these most recent papers, but I've seen these titles pop up. Let's look at all the classics. What if we go to representation theory? Probably a lot of the same papers. We got some physics stuff. Heisenberg algebra of a vector space. We decategorify the Heisenberg 2 category. What the hell? I never even knew it was categorified in the first place. I haven't looked at the representation theory thread for a while. Non-Archimedean Hitchin map. What? Okay, that looks freaky. Let's take a look at that. Jesse, we need to cook. That's why we're here. That's why we're on ArXiv. It's time to cook. Yeah. Infinity category stuff. Abstract representation theory via coherent Ausander-Reiten diagrams. Okay, I want to take a look at this too, actually. Hello, Rod. Good morning. Yeah, let's look at these for now. This looks good for now. Let's have ourselves a little look-see here. The Heisenberg algebra of a vector space and Hochschild homology. Crazy. Big latency is back? Oh, I guess so. I don't know. I was having a lot of troubles with OBS this morning. I tried starting stream like 10 times and it told me I couldn't. And then I tried changing the stream passkey, but there wasn't even anywhere for me to put the new passkey, so but then it worked. I don't know, it crashes a lot too. Hello, Christian. Or Christian. Or no, I'm not even reading that carefully enough. CHTRIS Tristian. Tristian. Sorry about that. Okay, let's see. What the hell is going on here? Whoa, this looks crazy. The Heisenberg algebra originated in quantum mechanics to describe the commutation relations between position and momentum. The infinite dimensional Heisenberg algebra. Oh, I saw that infinity in my peripheral vision. I was like, oh, it's infinity categories, but no. Has generators and relations, part in many areas of math and physics, blah, blah, blah. And we have this result. Smooth projective surface. Hilbert scheme. I don't even know what that is. Differential geometry coded. Hell yeah. Chi is the pairing given by cup. And the direct image along the point. For every cohomology thing, there are operators. That blah, 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 blah. Okay, that was crazy. Sure. Whatever you say, bro. Oh, because ugly notation, I see. Here, the Heisenberg algebra of a graded vector space with a symmetric bilinear form is a generalization introduced there. It has generators, relations, creation, annihilation operators. Okay. In this paper, we generalize this to all smooth and proper non-commutative varieties. I don't even know what the right definition of a non-commutative variety is. I thought a non-commutative variety was just like a category of modules or something. This is crazy. What's my opinion on actuarial science? Well, I probably should have done that when I was younger, so now I'd be rich. That's my opinion. If I could choose to become an overnight expert in some topic, what would it be? For you, it's definitely combinatorics. You're scared of them. I would choose to become an overnight expert in investing my money and getting good returns on it. Because then I would just spend, then I would just make a living off of investing and playing the stock markets, and then spend the rest of the time doing abstract nonsense. That's what I would do. But, okay, if we take this to be more about pure mathematics, what do I want to become an overnight expert in? I guess, categorical local Langlands, probably. Whatever the hottest stuff is right now, I guess, so that I could publish papers on it and people would think I'm hot stuff, right? Google Egorychev method. Boring answer, you meant with math topic. Yeah, well, categorical local Langlands or something. Egorychev method. For finding binomial coefficients. Oh. That's cute. That's a nifty little thing there. Probably more than just cute. I mean, I'm sure this idea generalizes to do some sort of fancy, I know that there's crazy generating series combinatoric stuff that you can do by using some complex analysis things. So, oh, well, Boris, you're too kind. Yeah. Smooth and proper DG category. Oh, okay. So we are basically doing infinity category stuff. DG category over an algebraically closed field characteristic 0. Euler pairing on Hochschild homology of a category of it. Oh, the DG category. Jesus, I don't even know what's going on. Some blood. Written a 600-page book solving combinatorics problems. With this, it's on wiki references. Oh, with this method. Just basically this one method, and it's just like I'm gonna push this. Is it in these references here? Just like, hey, I'm gonna push this method to the max. That's kind of based. It's a little bit based, one could say. Yeah, this is crazy stuff. I mean, is that what is a non-commutative scheme? Wait, yeah, what's that mean to be a proper DG, a smooth DG category? Is that what a non-commutative space is these days? What is the definition of a non-commutative? Did he say scheme or space? Varieties. Okay. Non-commutative. Let's say variety. I mean scheme, variety, whatever. No single simple definition. Okay, so then what are they talking about in this paper? Approaches to definition. Derived category approach. Prominent approach defines a non-commutative variety entirely in terms of its corresponding derived category of coherent sheaves. Okay. Defines non-commutative variety. I see. Over the relevant algebra. Okay. Sure. I do want to look into this. You know, my rings and modules. I've got next week. I finally am in a place where my my next categories of module videos is going to come out. I've got, you can see pages of script here, because I'm gonna record the next video soon. And anyways, I wanna definitely move towards understanding things about categories of module, and then maybe eventually like derived categories, derived Morita equivalence. But I'm just really breaking down basic Morita equivalence first. So non-commutative geometry comes in many flavors. Here we follow this, where a non-commutative scheme. Okay, so a non-commutative scheme is defined to be a DG category considered up to Morita equivalence. Such an A can be viewed as a DG enhanced triangulated category. The triangulated category enhanced by A is this. Hello, Kostaka Kori. The compact derived category of A modules. If A is a commutative algebra viewed as a DG category, then this is the compact derived category of quasi-coherent sheaves on the scheme. Crazy. Right. So the point of this approach is that we take any enhanced triangulated category. Okay, wait a second. Maybe I need to read this again. Okay, so the perspective is that a non-commutative scheme is a small DG or A infinity category A. So A is a category. Such an A can be viewed as a DG enhanced triangulated category. If A is a commutative algebra, what viewed as a category with a single object? A DG category with a single object? Yeah, okay. What's the T on Morita equivalence? You just know it's a ring with equivalence of categories of modules. Yeah, that's basically it. That's basically two rings are Morita equivalent, if and only if their module categories are equivalent. And I think it's an interesting thing. But, I've read this line that I've complained about this on my channel before. I read this line. Someone said, this is like in a Stack Exchange answer. They're like, because now people consider derived Morita equivalence. So not necessarily Morita equivalence of the categories of modules, but of the derived categories. And, someone said, they're like, oh, ordinary Morita equivalence isn't very interesting because, like, you can't even change the dimension of the objects or something. And I don't know. To me, it's still very interesting. To me, it's still very, very interesting. Like, so, one thing I was thinking about, and this actually comes from my research. This was like a problem with this was a problem I was running into in my research, that I found a different way around in my most recent preprint. But, there's this problem I've talked about before of, like, you have an isomorphism of rings, and we want to know things about how, like, the multiplicities of simple modules of A, how they show up in certain other modules. And so we've answered that similar question for B, but now the question is, well, you take a simple module and you take the restriction of scalars over into the category A, but you want to know, like, if we have names, right, some explicit construction of the simples for the ring B, we want to be able to precisely articulate which simple, like, pi I gets sent to in terms of, like, some alternative classification for the simples of A, right? And so for me, this is like a very big problem, right? Or like as I've phrased it before, imagine you have two groups and they're isomorphic, right? Or like, right? Imagine you have two groups and you classify all the irreducible representations of this group, and your colleague goes and classifies all the irreducible representations of this group. But these are very complicated groups, and only later do you find out that they're isomorphic. Well, the question is, which E-rep goes to which E-rep, right? Or another way to phrase this is to take the automorphism group of your group and just realize that it acts on the set of irreducible representations of your group under, it takes an irreducible representation and just, like, precomposes with an automorphism. So, like, what is the orbit structure on there? I think that's an interesting question. Originally born out of an issue in my research, but now I'm just kind of like, well, what does that mean? So I mean, this is even beneath and this isn't even considering other functors that come from Morita equivalence. But okay, there's some nice theorems with K0 for them. I don't know about those nice theorems. Morita equivalence stuff has the same module, rep theory, quasi-coherent sheaf theory, yeah. Your spidey senses are telling you there's some model theory business in the background. Well, I know nothing about that. So, but sure, why not? Why not? Yeah, I mean, I don't know if anyone cares about this, but like, I do want to spend time. Like, I don't know, just writing out examples of finite groups and computing the structure of the orbits of the automorphism group on its set of irreducible representations. That just seems interesting to me. Algebraic K-theory of rings is defined in terms of their module categories, so of course it's Morita invariant, I see. Number of geometrical features can be read off at this level. Just came across this channel. How did I get into math and decided to pursue a PhD? I think in some sense I've always been into math, but I didn't know that I was into math, if that makes sense. Like, I was always thinking about shape and number. Not that I was, good at it. It's not like I had some hidden talent when I was really young. But, I remember being really excited when my mom first explained how, like, solving 5 plus x equals 2 works. And then sometime in high school, I started smoking weed, and I was like, whoa, man, like, the universe and stuff. It's like, what's going on, And then I started reading pop physics books, and then I read all the pop physics books that there was at the time, and then I realized I still didn't understand things well enough. And then I realized the reason I didn't understand things well enough is that I had to learn math. So then I kept failing math, but then I started teaching myself calculus. And then at some point later on, I got my head out of my ass, and I started going to university seriously for mathematics, and I just kind of fell in love with math on the way, and that was basically it. I never really decided to do a PhD. I was just sort of like, well, I like math, I want to keep doing math. And it was just sort of like, that's just what you do if you want to keep doing math. What you're trying to remember is that A and M and A are Morita equivalent. Yes. That gives you some cute proofs of K-naught of basic algebras. Oh, because if you want to compute K, you're saying you can use that to compute K-naught of M and A by just computing K-naught of A. I see. Geometrical features can be read off at this abstract level. Smoothness, properness, differential form. Differential forms? What? Wow. Beautiful summary is given in 2021. Well, one might be tempted to work with more sophisticated enhancements, but for the present paper suffices. Okay. I'm going to keep this paper open because this seems not only interesting, but also seems to have some good references to other sources. I'm glad it was inspiring. I love that the introduction is just like the most complicated shit in the world. Just like, oh, infinity DG category derived enhancement. We define and then and then preliminaries. Yeah, binomial coefficients. Yeah, we're going to define binomial coefficients for you. I mean, okay, to be fair, this is like a generalized binomial coefficient, but still. Kind of funny to me. But cool. I'm gonna keep this tab open. Let's see what else we got here. What's going on here? Let F be non-Archimedean valued field. Sigma a closed Riemann surface of genus at least 2, and gamma its fundamental group. Building on the theory of equivariant harmonic maps into R trees, we study the non-Archimedean Hitchin map from the SL2F character variety. What? Yeah, this is crazy. I have no idea what's going on here. The study of representations of surface groups into Lie groups has deep connections with complex geometry, low-dimensional topology, and dynamical systems. For a closed Riemann surfaces genus, classical non-abelian Hodge theory, reductive representations. Whoa. Okay, I don't understand anything that's happening. Seems cool. This is all too far beyond me. Let's have a little look-see here. Abstract representation theory via these diagrams. Provide a general method to study representations of quivers over abstract stable homotopy theories. Over homotopy theories? Jesus. Representation of quiver over a homotopy theory? What the hell does this mean? Jesus. That's the nature of math research now. Even if the concepts might not be so complicated, even the terminology is a barrier. Yeah. Yeah, that's true. For a finite acyclic quiver and a stable infinity category, we prove an abstract equivalence of the representations. So representations of a quiver into an infinity category with a certain mesh infinity category. Ooh, universal auto equivalences. That seems kind of interesting. Ooh, a spectral Picard group. No idea what this is, but it seems interesting. Yeah, I'm sure I could grasp these things. But yeah. I agree the leanification of math will be beautiful, Boris, although I don't know if that's going to help one jump into a subject any faster than before. Although maybe, because it really gives you a very clear, right? Like if there's some fancy theorem, gives you a very clear, like you can just work the tree backwards to understand everything it depends on. So, okay. Introduction. Let's read the introduction. Let's get a little more of a sense of what is going on here. Also, a good tip you once got: the introduction of a paper is the hardest part. You shouldn't start there. What? Yeah, I disagree. The introduction, I don't know. Maybe that's true. But I mean, the introduction, I feel like the introduction is like the only part you read. So you understand what the hell's going on, and then, and then you just scroll down to see, oh, okay, they wrote a proof. Okay, great. One of the best understood examples of derived categories is the derived category of representations of a quiver. Is that so? This is largely due to Happel's work and uses methods coming from representation theory. Oh, Rod, you're in undergrad? Jesus Christ, man, we're all cooked. If you're an undergrad, Jesus, we're all cooked. What, are you going to Harvard? You should be going to Harvard, Arad. You always skip the 100-page long introductions in your Penguin Classics. Yeah, I mean, that's an introduction worth skipping. Yeah. Anyway, this guy uses Auslander-Riemann theory to find quite explicit combinatorial descriptions of such categories. Oh, that is interesting. Yeah, that was not on my bingo card either. Yeah. Encoded in the Auslander-Riemann quiver. Oh, wow. So you take a quiver, you take its algebra, you take its derived category, and then you get a new quiver that describes the derived category. And what happens if you take the derived category of that new take the quiver algebra of that? Wow, that's very interesting. For instance, it reveals that derived equivalent quivers must have the same unoriented underlying graph. Very interesting. Moreover, relevant functors can be read from this quiver. Reflection functors, Hare functors, suspension. Namely the derived Picard group. Crazy. However, beyond the setting of representations over field, little is known when considering more general coefficients, such as integers or arbitrary commutative rings. Our approach to the subject is rather radical but well-founded. It has recently been observed that certain well-known symmetries of categories of representations are actually mere consequences of the stability, in the sense of homotopy, of the categories involved. What? Man, what? This is cool. In the sense of Groth? Is this like the Pokemon that evolves into Grothendieck? In particular, we aim to introduce techniques from Auslander-Riemann theory into the study of categories of representations over abstract, stable homotopy theories. Whoa. What? What does that even mean? There are several approximations to formalizing the abstract notion of stable homotopy theory. The most classical one of a triangulated category fails badly for our purposes. Moreover, they lack the lack of essential functoriality properties in such categories obstructs some of the most fundamental constructions in representation theory. Choose to work within stable infinity categories. Wow, this is crazy. How does one motivate Picard groups? You've only seen them pop up in K-naught of Dedekind domains. I mean, that's a great motivation, if you ask me, as someone who's interested in number theory. Like the ideal class group is the ideal group. I don't know. I think that's a pretty cool group. Yeah, I don't know how does a geometer justify it? I don't know. This is a very, very post hoc definition. But speaking of, and I know probably some of you have heard these things many times before, but for a commutative ring, there's this paper that tells you that the automorphism group of the module category of R, of course, where I mean automorphism group, I mean up to isomorphism of functors, is, gosh, and I always, which one's the normal subgroup? I'm always think I'm getting it backwards, but it's sort of this extra piece. So I guess another way to justify the Picard group is that it measures, for a commutative ring, it measures how far away the automorphisms of the ring are from composing all autoequivalences of your categories. Line bundles also encode intersections of divisors. Well, there you go. There's the geometer's perspective. Do you offer one-off answer sessions instead of long-term tutoring? I don't know. What do you mean? What's a one-off answer session? Oh, you mean just like just meet for one tutoring session? Sure. Yeah. I mean, I have, I tutor most of the people I tutor, I would say, book me for regular sessions, but there's no reason why we couldn't just meet once, if you wanted. Yeah. And it coincides with H1 with coefficients in GM. Right. This is true in general. Picard is like what, of a arbitrary scheme or something? I vaguely recall seeing something like this. I wonder if that's a hint for more general definitions of a Picard group. This is something I've seen before. Ooh, yeah. Because I remember in like Lamb's book, he's talking about, defining Picard group for non-commutative rings. And I've seen some discussion online that suggests there's a couple different ways that you could define it. But actually, this thing here, not even just in schemes. Wait, not even just in schemes? Oh, also for I see. Yeah. But this suggests that one could define the Picard group for a general ring to be just this quotient. Although, is it true that this is always normal in here? I think so, right? Because let's say F was an autoequivalence. Wait a second. Let me go back. Hello, on piece music. Hello. What does Picard group do for us mere mortals? It tells you have unique factorization in your ring. So like how the integers can be uniquely factored into prime numbers. Or rather, it gives you a measurement of how badly that fails. Something like this. If you have a semi-direct product, then ought R has to be normal. Yes, but in the hello, Mr. L. But ought R, I mean, we only know that it's a semi-direct product in the case that R is a commutative ring. We only know that's a semi-direct product in the case it's a commutative ring. So yeah, this is why I get confused, because some people do it this weirdo oddball way. So the Picard group is actually the normal subgroup. So I guess the thing to prove would be, so I guess here's another way we could define it is like, so if the automorphism group of the module category, if we can prove that surjects onto the automorphism, if we can create a surjection onto the automorphism group of the ring, then we could define the Picard group of the ring to be the kernel. And this is better because actually now one doesn't need to worry about normality doesn't need, because here it's just if we have this quotient, we could define this quotient. So their hands are waving at it. That's a funny way to remember. I mean, the way that I remember it is just like this is the notation for the normal subgroup, and so you're just taking this triangle and then extending the lines. But yeah, that's a more fun way to remember it. But it's very weird to me, right? It's very weird to me because no one in their right mind would ever write normal subgroup like this. So why in the hell would you ever write the semi-direct product like this? I don't know. Whatever. I guess, yeah, I don't know. It's still kind of weird to me, but whatever. If I like all the category level stuff, you should look into L-adic Fourier transforms. Yes. I mean, I have looked into, there's this book with a very famous typo in the title. Instead of L-adic, they spell it Ladic, but it's Perverse Sheaves and the Ladic Fourier transform. I've definitely spent a little bit of time with that book because of the relevance of perverse sheaves to my research. Why would you ever work with non-commutative rings? Because I'm not a little baby child. Commutative rings, all of algebraic geometry. This is child's play, little baby children's work. And I'm a real man, and real men only work with non-commutative rings. You couldn't remember the direction? Now you can. Nice. You read it like that? Leo lectures? Wait, you read it the wrong way? Gross. Non-commutative something homotopy. Hell yeah. You could see people writing normal subgroups right to left. The short exact sequence, yes, I agree. Although, I mean, to be fair on piece music, no one's preventing people from writing the short exact sequence the other way around, I mean, except for the short exact sequence police, but they're easy to evade. Yeah. To be honest, you're a universal algebraist, so you're more of a man than Ulysses. Imagine assuming you have operations at all. Wow, that's true. Damn, I gotta get I gotta get my T levels up to the level of a universal algebraist. Damn. Have I ever worked with Dahas? No, not really. I mean, they intersect with my reach. I work with affine Heck algebras, but and so I've come across papers on double affine Heck algebras, but yeah, it's never so far hasn't particularly played into my research. But I don't know. Maybe if I look more into those papers, there's something there for me. Yeah, he's got long personality. Yeah. Okay, I think I might leave it there for today. I gotta go to campus. I gotta meet with my supervisor. I think I might try and do a run before I go. But yeah, have I ever worked at all? Called out in chat here. The evolution of universal algebraist is a multi-universal algebraist. Don't you mean inter-universal Tech-Mueller theorist? Anywho, yeah, that's where we're gonna leave it for today with these very interesting papers. Yeah, sorry, Leo. I started early today, cause rise and grind, baby, cause that's why. Okay. I'll see y'all tomorrow though. And QED.